equilibrium, most players choose S all the time. Okay? Okay, that's the case for our answer for the case t equals to 2. Then what if t is 3? Actually the same answer, right? Our answer should be the same. Why? We know that in the last period, the outcome will be S and S, right? And in the second last period, we already shown that, check that outcome is also S and S in the second last period. And given that in the first period, S and S is the only equilibrium outcome in the first period as well. Okay? And then actually that's the case for any capital T as long as T is finite. Okay, so our answer for this finite repeatedly prisoner's dilemma case is pretty not really good, right? Not really satisfactory. But maybe it is simply because the game is repeatedly finitely many times only. Okay, so let's see what happens if game is infinitely repeated. Okay, so there is repeatedly, capital T is basically infinite. So which means that they play this game forever. Okay, and this counting factor has to be, and let's say this count, Okay, so let's say now this game is repeatedly played forever. Okay, so here, if we want to consider repeat game, infinitely repeated game, we have to assume that this counting factor is strictly less than 1. So remember, actually, maybe you didn't really pay too much attention here, but when we talk about finitely repeated game, we allow that actually, delta to be exactly equal to 1. Right? I mean, in this case, in finitely repeated game, we allowed even delta is equal to 1. But if you really want to think about infinitely repeated game, you have to assume that delta is actually strictly less than 1. Okay, so that's kind of technology we have to take care of. Why? What happens if delta is exactly equal to 1? The reason is that, the technical reason we have to restrict attention to the case delta strictly less than 1 is, if delta is exactly equal to 1, then payoff, the sum of payoff will be infinite. Right? Let's say, player 1 gets payoff equal to 1 in every period. So then the final payoff will be 1 plus 1 plus 1 plus 1 plus basically forever. And that's going to be infinite, right? The real problem is that, okay, so let's consider the other case that player 1 gets payoff 3 all the time. Then if you sum 3 plus 3 plus 3 plus 3 plus 3, then that's also infinite, right? So, sum of, we are comparing two cases. In the first case, player 1 gets payoff equal to 1 in all periods. And in the second case, player 1 gets payoff equal to 3 in all cases. But the outcome, the total payoff is infinite in both cases. Then it's not really clear how we can compare infinite and infinite, right? So in order to check whether something is equilibrium or not, we have to compare payoffs in two different cases, right? But if delta is 1, then 1 you have on the left-hand side of inequality will be infinite, and 1 you have in the other side of inequality will be also infinite. And so it's a totally nonsense, mathematically nonsense, to compare infinite and infinite together. So to avoid that case, we need this technical assumption delta is strictly less than 1. If we really want to think of infinitely repeated game. Okay, so that's just small technology. Okay, so then actually if you consider this infinitely repeated game, infinitely repeated prisoner's dilemma, actually you can construct a sub-game professional equilibrium such that both players choose S all the time on the equilibrium path. So there is kind of dramatic difference between finitely repeated game and infinitely repeated game. If game is finitely repeated, then outcome is S and S in all equilibrium. But if the game is infinitely repeated, then there is at least one equilibrium such that S is played all the time, at least on the equilibrium. Okay? Okay, so how then? How come? So this is my proposal of, so let's consider this strategy on the screen. So remember again that we have to specify which action to take in all possible cases. Okay? So this strategy profile tells that, okay, so both players choose E in the first period. So they begin with E in the first period. And then continue to do so. So continue to choose E in every subsequent period, as long as both players have chosen E in all previous periods. Okay? So it's like, we begin with effort and effort, cooperation together, and as long as, cooperation continues, we will continue to cooperate in the following period as well. Okay? So that's what happens on the equilibrium test. But our strategy also has to specify what happens if one player deviates, right? And the second bullet point here is about that case. So it says that choose S shirk in all other circumstances, which means that as soon as one player deviates, then both of them choose S in all subsequent speed. Okay? So summing up, this strategy tells that we are going to cooperate together on the equilibrium path, but if any deviation is detected, then we are going to play S all the time. Okay? So in other words, a single shirk of either player triggers, as you can see on the screen, triggers the perpetual shirk of both players. So some economists call this kind of equilibrium trigger equilibrium for the obvious reason. Any deviation triggers really bad outcome. Okay, so let's check whether this is really equilibrium or not. Okay, so first of all, this is infinitely repeated game, and that means that we cannot really use the backward induction, right? I mean, in order to apply backward induction, we have to have clear point, clear final moments in the game. But here, the game is repeatedly played forever, so there is no really final moment in this game. So we cannot apply backward induction. Okay? So however, we can still apply one-shot deviation principle. Okay, so we have to show that no player has profitable deviation in all cases. Okay? So let's begin with the case described in the second bullet point. Okay, so what the second bullet point basically tells that, let me repeat myself one more time. Once a deviation is detected, we're gonna play S and S forever, right? So we are thinking of the sub-game that follows any detection of deviation. Okay, we have to make sure that restricting our strategy in that subgame, our strategy is still equilibrium in that subgame, right? And intuitively speaking, it amounts to showing that whether they really have incentive to follow this perpetual shark of both players in that subgame, right? I mean, the strategy profile, suggests that you have to shirk all the time once deviation is detected. But of course, we have to make sure that indeed they have incentive to follow that suggestion, right? So in other words, okay, so let me put slightly different way. So basically, this second bullet point tells that once shirk is detected, we are gonna punish, right? Mutually punish all the time. But we also have to check we really have good incentive to punish, because punishment sometimes also hurts me. Okay? Okay, so let's check that. But actually, that's not really difficult to check that. Here in this subgame, okay, so let's think about player one's perspective. Okay, so player one understands that in that subgame, player two will choose S all the time. Then exactly the same reasons, same argument we used for the case finitely repeated prisoner's dilemma game. Once player one understands that player two chooses S all the time, there is only best response for player one, which is S. Okay? So this part is okay. Okay? So we just have shown that as soon as they begin to mutually punish each other, there actually no player actually has incentive to deviate. Once they begin punishing mutually, then the best thing is I also punish. I mean, once I understand you will punish me, then my best response is I also punish you. Okay? Okay, so then what remains for us is, okay, so we also have to check whether either player has no incentive to deviate on the equilibrium test as well. Which means that we have to show that as long as we have been cooperating so far, I, player one, has no incentive to shirk. Okay? If think about what happens player one if player one shirk. Player one, his payoff increases and is temporarily. Right? I mean, in this period, if I follow equilibrium strategy, we're going to play E and E. So my payoff is 2. But if I deviate and shirk, then my payoff will increase at least in this moment, in this period, from 2 to 4. Right? So there is kind of short-term benefit from shirking. Right? But at the same time, if I shirk this period, then I'm going to lose the whole chance of cooperation in following periods. So that's this utility from shirking, right? So kind of cost of shirking in this period. So you have to compare that benefit and cost and make sure that benefit is larger than cost. Okay, so let's check carefully that. So if I follow equilibrium strategy, so let's say it is period 2t. Then if player one chooses E, then what happens? So my payoff will be suppose player one chooses E all the time. Okay? Then my payoff will be this, right? So E is the payoff from cooperation in prisoner's dilemma game. So in the first period, S is periods, index for the periods here. So in the first period, I have delta to the 0 times 2 in the first period as my payoff, which is 2. And in the second period, my second period payoff is discounted. So indeed, if you plug S equal to 2 here, then my payoff realized in the second period is delta times 2. If you plug S equal to 3, then this term will be delta squared times 2. So that's the payoff realized in the third period, etc. Okay? So if player 1 chooses E all the time, then this is the final payoff. Okay? Okay, now suppose player 1 chooses S in period T. Okay? Then what happens? What is payoff? So first of all, we already have cooperated up to period T minus 1, right? And my payoff from that cooperation is 2. I mean this thing, okay? So this is payoff already realized, okay? So if I deviate, in period T, then still I enjoy this payoff, right? I mean, it does not really change. Anything happened before my deviation. I think I have to be more careful here. Choose in period 1 to T minus 1, and then choose this as in period. Okay? Okay, so that's payoff realized before my deviation. And if I deviate in period T, then my payoff will be 3, right? So if I deviate, my payoff will be 3 because the other player is choosing E still, right? So in this period T, if you think about what happens in period T, player 2 thought player 1 will choose E, right? But player 1 deviates, which means that player 2 still chooses E, but player 1 chooses S. So payoff realized in period T is 3. Of course, we have to discount. Okay? E minus 1. So I just plug S equal to T. Okay? Okay, then what happens in the following period? In the following period, both of them play S. However, which means that there is no more payoff. Okay? Okay, then we have to compare this payoff and this payoff, and we have to make sure that this is larger than this one. Okay? Then means player 1 has no incentive to deviate. Okay, so let's compute this one first. So this is the sum of infinite sum, and we know the formula for this kind of sum, right? So this is actually equal to 2 times summation of delta to the minus S minus 1, and this is equal to 2 times 1 minus delta times over 1 over 1 minus delta. Okay, so the first term here is 1, right? If you plug S equal to 1, the first term is 1. So we have 1 here, as a numerator, and the denominator is 1 minus delta. Okay, so 2 times 1 over 1 minus delta, which is 2 over 1 minus delta. Okay? Okay, what about this case? So here, this term is, okay, so this is equal to 2 times S minus, S from 1 to T minus 1, delta to the S minus 1. And we know that this is equal to 2 times 1 minus, so there are t minus 1 terms here. So 1, and the first term is 1 again. So we have 1 times 1 minus delta to the t minus 1, right? And 1 over delta. And this is delta to the t minus 1. So this is equal to 2 okay. Okay, so this is equal to actually, there are 2 terms here. So this is equal to 2 over 1 minus delta minus 2 over 1 delta to the t minus 1 divided by 1 minus delta plus okay. I just separate this term into two subterms, right? There are 2 minus 2 times delta to the minus t minus 1. So I have 2 here, 2 times delta to the t minus 1. Okay? I just did some algebra here. Okay? And any question or anything wrong here? Maybe I can make some mistake whenever I have to do some algebra on the board. If you found any error, just let me know. Hopefully this is correct. There should be 3 here. I see. Thank you. Yeah. Okay. So the first thing you can easily check is, if delta is very close to 1, this thing is always larger than this thing. Why? Because we have 2 over 1 minus delta and 2 over 1 minus delta here and here, right? So which means that in order to make sure this one is larger than this one, we only have to show that this term plus this term is negative, right? We have the same term here and here, so if the remaining term here is negative, that means this is larger than this. Okay? But if you think about what happens as delta goes to 1, then it goes to 3, right? As delta goes to 1, it goes to 3. But here, denominator goes to 0, which means that this term will go to negative infinity. So which means that if delta is sufficiently close to 1, this is always larger than the payoff from the deviation. Okay? So indeed, actually, you can show that if you do a little bit more work, indeed, it should actually suffice to assume that delta is larger than 1/3. As long as delta is larger than 1/3, then actually the first payoff here is larger than second period for any small t. So which means that player 1 has no incentive to deviate as long as delta is larger than 1 over 3. Okay? And the game is symmetric, right? I mean, if you calculate the same payoff for player 2, the calculation has to be exactly the same, right? So which means that as long as delta is larger than 1/3, then this is in the subgame property. question? Okay. Okay, so this is just one example, but really interesting, right? I mean, there are two interesting here. First of all, even if the prisoner's dilemma is repeatedly played, as long as it is finitely repeated prisoner's dilemma, there is no cooperation. However, if the game is repeated forever, then certainly there is some possibility of cooperation. Okay? And the basic intuitive story behind it is actually exactly the same, as the first example. Here, whenever they deviate, they punish with each other, and if delta is sufficiently close to 1, so that means both players are sufficiently patient. Then if they are sufficiently patient, then that also means that they care a lot about the future, right? So that means that any temporary payoff from my deviation in period 2, period t is less than my cost. The what I lose, in the future, right? Because one deviation means there is no more chance of cooperation forever. So if delta is close to 1, that means future is relatively more important than today. Okay? So that's the reason we need delta is sufficiently large in order to make sure that this is equilibrium. Okay, so let me make one more comment. Again, if you think about this game, infinitely repeated prisoner's dilemma, there are multiple equilibria actually. This is not only equilibrium. So for example, think about equilibrium strategy such that they play S all the time. Like the previous case, for the finitely repeated game. Let's say, let's say they choose S all the time in infinitely repeated prisoner's dilemma. Then, okay, so that's actually sub-game perfect equilibrium. Why? Because, okay, again, let's think about player 1's perspective first. So player 1 understands that player 2 will choose S all the time. Then again, it's kind of straightforward that player 1 also has no reason to put some effort. So S all the time is also best response for me in any sub-game. And the same thing for player 2. So which means that S all the time is also a sub-game. Okay, so we just covered 3 examples of repeated game. The simple example, the first simple example here, alpha and beta example, and we also consider repeated prisoner's dilemma, such that capital T is finite, and lastly we also consider the same repeated prisoner's dilemma, where the repetition is, the capital T is infinite. Okay. So I don't really want to give you any general theory of repeated game, but here, the thing I really want to convey is the point I really make here is that there is a huge difference. Sometimes there is a huge difference between just one normal form game and playing the same normal form game many times. Okay, so that's the first distinction I like to highlight here, and also. The other distinction I want to highlight here is there is also sometimes huge distinction between finitely repeated game and infinitely repeated game, like the case of prisoner's dilemma. Okay. Okay, so if you have some interest about general discussion in repeated game, then I also provide some references here. And if you need further references, then you can come to me, because there is also even a very thick book all about repeated game. So if you if you want some serious reference, I can also give the title of that. Okay, so if you have no questions, then let's take a break until 7:30. Okay.
我留着吃。动了，他说几点上课啊？待会儿休息会儿。你什么都没理，上课玩的7点半。